All participants are requested to kindly join the session. Your session has been going to start very soon.
हेलो हाँ सर आ रही है सर आ रही है सर ज्वाइन हो रही है
All participants are requested to kindly join the session. Your session has been going to start very soon.
सर जूम से करवा रहे हैं हेलो
उसके चक्कर में
आ रहे टॉयलेट
Good evening, everyone. Our respected resource person has been joined up in this meeting. I would like to request to all the participants kindly join the session, please. Your session is going to be started very soon. Good evening, everyone. Our respected resource person has been joined up in this meeting. I would like to request to all the participants kindly join the session, please. Good evening, everyone. Am I audible to everyone?
Yes, sir.
Voice is clear. Tushar sir, am I audible?
My voice is audible, sir?
audible and clear
Hello?
Yes, sir.
My voice is audible?
Yes, sir.
yes sir yes
Okay.
Okay, so let's start this session. I am Desh Deepak. Once again, welcome you all. The participant has been joined up in this Faculty Development Program 2025 has been originated in Sri Satya Sai University of Technology and Medical Sciences, Sehore. And on the behalf of Sri Satya Sai University of Technology and Medical Sciences, we are welcome to all the participants has been joined up in this session. And the topic for the today's session is green hydrogen and future of renewable energy system. This is one of its kind faculty development program going to organize through the School of Engineering of SSS CTMS COR. And we are really thankful to our Honorable Vice Chancellor Dr. Mukesh Tiwari sir. Under his leadership and continuous support, this kind of program has been originated in this university timely and accordingly. Now this is one of its kind. We are really thankful to the uh, coordinator of this program, Dr. Sachin Kumar Baraskar sir, who has been the main coordinator of this program. Also the co-coordinator of this program, Mr. Manoj Kumar Ganwane sir, who was the co-coordinator of this faculty development program. Also, we would like to thank the research director, Dr. Mohit Gangwa sir, also the School of Engineering Dean, Dr. Rajan Singh Kuswa sir, and also the behind the curtain, the support of Dr. Santosh Kumar Rai sir, who has been beautifully designed and originated and supported from back end to originate this faculty development program in our university. I would like to request to all the participants kindly join this session, which was taken up by our honorable, respected guest, Dr. Tushar Chaudhary. Your attendance has been marked up through the session who has been joined up in this session. So once again, I request to all the participants kindly join the session so that you can utilize the knowledge, the information, the productivity which was shared up by very soon by Dr. Tushar Chaudhary sir. Now, sir, can we proceed? Tushar sir, if you allow me to.
Yeah,
Yeah,
yeah.
we can proceed
On the
with
behalf of
the.
Sri Satsai University, we welcome you, sir.
Thank you
For
for
giving
giving
us
me
a
the
valuable
opportunity.
for giving us valuable time to sharing your thoughts, your ideas on this faculty development program, and we wish that your ideas and your thoughts on the topics has been very useful to all the participants has been joined up in this session. Now, Tushar sir, over to you, sir. You can carry forward from here, sir. Uh,
My screen is visible.
no, sir, not visible. Yes, sir. About Tushar sir, I would like to say something that Dr. Tushar Chaudhary sir has a PhD from NIT Jamshedpur and he has an ME from Mechanical Design. Also, he has a gold medalist. Currently, he is an assistant professor in Department of Mechanical Engineering and a principal investigator in Sustainable Energy Technology Laboratory. PDPM Indian Institute of Information Technology Design and Manufacturing, Jabalpur, Madhya Pradesh. Now, the next further introduction has been given up by Tushar sir also. So from here, Tushar sir, you can continue. Once again, welcome you, sir.
Thank you for such a brief introduction over here. So, shall we start the session, sir?
Sure, sir, sure.
My screen is visible, sir.
Yes, yes, sir.
So, good evening to all of you. So, today's session, I'm going to speak about the advanced hydrogen energy system, where we are going to cover the aspect associated with the production technology and its sustainability challenges associated with this. So, before starting, I first of all thank you to the organizing committee of Sri Satya Sai University Technology and Medical Sciences, Sehore, Madhya Pradesh. And here, the entire organizing committee and the Department of Mechanical Engineer who have taken initiative for this AICT Atal training by the academy over here. So, the learning objective associated with this, we are going to have the development of concept of hydrogen energy, method of hydrogen production, and storage of hydrogen. So before starting, first we are going to have the introduction of what is basically a hydrogen energy. So hydrogen energy is one of the most promising uh, form of energy derived from the hydrogen gas, and it is going to be attracted since it's increasing attention as a potential solution to environment and the energy challenges. So the hydrogen is one of the lightest and most abundant element in the universe, and it can produce through various methods and has a versified application in the area of transportation, power generation, and the industry and the heating aspect over here.
सर
So it's
वॉइस इको कर रही है बहुत.
include the zero emission when it is going to be produced when by means of renewable energy storage capabilities, and have a versatility over here. So some challenges associated with the production efficiency, storage, um, cost, we are going to address over here, and to full harness its potential in the transition to the sustainable energy future we are going to discuss. So in this we are trying to discuss the key aspect associated with the hydrogen so that you can able to understand
सर
that
वॉइस बहुत इको कर रही है.
full potential of the hydrogen has not been.
Sorry to interrupt you, sir. Tushar sir.
Yeah,
One of our participant has been complaining that your voice has been a lot of echo.
wait a minute, is it okay now?
Is it okay to everyone?
Okay, okay.
Yes, sir. You can proceed from here.
Yeah, actually, parallelly I have tried to log in it via my cell
Oh,
phone, so therefore it is little bit
yes, sir.
echoing. Sorry
Yes,
for
sir.
the interruption.
No issue, sir. You can proceed from here.
Okay, so here these are the main introduction associated with the hydrogen energy. Now we are going to discuss about the key features associated with the hydrogen over here. So the key salient feature about the hydrogen here we have. So within this, first, we have it is one of the most abundant element in the universe, and making up about 75% of its elemental mass. Then clean energy, when it is used as a fuel, the hydrogen produces only from the water vapor as a byproduct, and making it as a clean and environmental friendly energy source. And in terms of versatility, I'm going to talk about the hydrogen can be used in various sectors associated with the transportation, power generation, industry, or heating, offering a versatile solution for the reducing the carbon footprints and emission. Fourth, that is high energy density. That hydrogen is having a energy to weight ratio is going to be quite high, and making it as one of the most excellent energy carrier for wide range of application. And in terms of zero greenhouse gas emission, if we are going to talk about when it is going to be produced via renewable energy sources, hydrogen has a zero greenhouse emission gases, which is going to contribute to effort to combat the climate change in near future. And in terms of energy storage, I'm going to talk about the hydrogen can be stored for a longer period and used when it is going to be required, and making it as one of the valuable asset. I'm talking about asset in terms of energy storage solution for a intermediate renewable energy sources. Then in terms of hydrogen fuel cell, I'm going to talk about that how it is going to have a potential for a renewable energy production. So fuel cell as a hydrogen fuel can be generated within the electricity and high efficiency and low emissions we are going to have. So suitable for a variety of application, which includes the stationary power generation and some challenges associated with this. We have the hydrogen production, energy intensity related to storage, transportation, and most important that here the cost that needs to be addressed, um, um, widespread adoption over here. Some potential renewable production, if we are going to talk about that, hydrogen is going to be one of the key energy source for the future, as hydrogen can be produced by means of electrolysis using renewable energy sources, just like a wind, solar. Therefore it is going to be referred as a green over here without having any carbon emission. So for industrial application, if we're going to talk about, the hydrogen is having various industrial processes, which includes the petrochemical production, steel manufacturing, and ammonia synthesis over here. So alternating to fuel, if you are going to talk about, the hydrogen can replace the fossil fuel for the heating and transportation and reduce the reliance on the carbon intense energy sources over here. So next, lastly, that in terms of infrastructure development and requirement, I'm going to talk about the adoption of hydrogen as a energy carrier requires a development of an specialized infrastructure for production, storage, and distribution. So these features makes the hydrogen as a promising candidate for the sustainable energy future, and particularly when produced and analyzed in a way that minimize the environmental impact and contribute to decarbonization of efforts over here. So next here, some methods, key methods I'm going to discuss about that, how this hydrogen production is going to be taken up. So generally the hydrogen production is carried out by means of different methods. So I'm going to concise it over here. So first, the hydrogen can be produced here by means of steam reforming method, electrolysis, thermochemical process, biological hydrogen production, photochemical water splitting, high temperature water splitting, hydrogen production from biomass, and hydrogen production from nuclear power, hydrogen production from solid oxide electrolysis cell. Each method have their own advantages and disadvantages. So here I'm going to explain the key advantages and disadvantages and major challenges associated with this, so that its sustainability aspect we are going to have it in this session, so that the new research line in the direction of adoption or deployment of the such type of methods and the technology associated with the hydrogen production, we are going to cover within this. So related to the production method, we first start with the steam reforming method. So this steam reforming method is widely used uh, in industries over here. So within this, we first have the hydrogen production from the natural gas, that is the methane, primary method for large scale hydrogen production, and is commonly employed in various industries, including chemical, manufacturing, petroleum, refining, and the hydrogen fuel production over here. So within this, you can see here, this is a schematic diagram where which show the methane reforming reaction. So how it is going to be work, that methane feedstock, which is a primary feedstock of an for generation of hydrogen by means of steam reforming reaction. So here natural gas, which is primarily consists of an methane. So this methane is typically extracted from the natural gases reserve or obtained by a byproduct of other processes such as oil refining. Then second, after this we have the steam generation. So steam is going to be generated by heating the water. The steam will going is an crucial reactant in the reforming process. So at a high temperature, steam provides the necessary energy for an endothermic reforming reaction. And once we have this reforming reaction in the form of uh, reactor here. So within this, the methane and the steams are introduced to an elevated temperature, which is roughly around 700 to 900 degrees centigrade within a moderate pressure. And the chemical reaction there is in form of endothermic we have. So based on that endothermic reaction, we are going to have the hydrogen production. So when the this reaction takes place, that the heat is going to be consumed, and in terms of absorbed it will going to have, and it converts the methane and steam into carbon monoxide and the hydrogen. Some other reaction also takes place over here, that is we called it as a water gas shift reaction, which is an exothermic in nature. And this reaction is exothermic, which helps to shift the carbon monoxide and the hydrogen ratio towards more hydrogen and less towards the carbon monoxide. Here we have an exchanger, heat exchanger, where the endothermic reaction absorbs the heat, which is typically provided by a combustion of a portion of natural gas and another fuel source. So heat exchangers are used to recover some of its heat to preheat the incoming reactant and the generated heat. Uh, Here, my voice is audible. Hello, sir. My voice is audible.
Yes, sir.
Yes,
Actually,
sir.
I think maybe some participants have put on their mic, so therefore some little bit noise is coming.
Okay, okay, sir. Let.
I request the admin to kindly mute it if possible.
Yes, sir. Sure.
Uh, is it I am facing the difficulty, or maybe participants are also facing the same issue?
No,
Yes, sir.
Yes,
Some
yes, sir.
mic is on.
Yes, sir.
I request admin to please take care of this so that every participants and maybe other over here, they can have a smooth interaction over here. Once they have any query, and they can switch off their mic and then they can speak it over here.
sure, sir. Sure, sir. We will
That will be
take care of
okay.
it.
So therefore, it's my just request over here. Uh, so
Sure,
so
sir.
shall we proceed?
Yes, sir. You can proceed, sir. I will
Yeah.
take care of it.
Okay. Okay. So related to heat exchanger, I have talked. So in terms of product separation, now after this, so the steam produced over here, that reformer contains the hydrogen and carbon monoxide and carbon dioxide and some form of unreacted methane we are also going to have. So various separation process which can be employed over, such as pressure swinging absorption or membrane separation, are used to purify the separated hydrogen from other gases over here. Carbon dioxide capture, I am going to talk about, which is an optional one, which is also generated during. So in some application, this carbon dioxide capture system may be integrated into process to reduce the greenhouse emission. And this is one of the important, especially if the hydrogen is intended to use for clean energy application or a fuel cell based vehicle for, or a hydrogen infrastructure in terms of export over here. So related to this, some byproducts we are going to have. So these byproduct utilization we can have, that in terms of carbon dioxide produced during this process can be utilized in various ways, such as enhanced oil recovery or in chemical process. So steam reforming is a well established method for hydrogen production, but it does not have um, does have, means some drawbacks we can, or some disadvantages over here. So it is an energy intensive due to the need of high temperature. So it produces the carbon dioxide as a byproduct and contribute greenhouse emission gases over. So research are still going on in this space, to develop more efficient and cleaner method for hydrogen production, such as electrolysis by means of renewable energy sources. So within our lab here in Triple ITDM Jabalpur, we have the technology over here where we are going to have the hydrogen production over here, which is a part of one of my research project, which has been funded by the SERB NRF over here. And within this, we are trying to generate a hydrogen, clean hydrogen from the waste heat of the engine over here. So we are planning to convert the existing diesel engine into a hydrogen one, and based on that, some research papers we have published in International Journal of Hydrogen Energy Fuel over there, along with the supplementation of the biodiesel. So our results are quite promising, and we are in the phase of developing retrofitted technology, retrofitted kit over here, where this hydrogen can be utilized in any diesel operating vehicle, so that significant amount of carbon footprints can be reduced to minimum. Next process I'm going to talk about, that is the electrolysis process. Electrolysis is a clean and green method of hydrogen production that use electricity to split the water into hydrogen and oxygen. So electrolysis requires an electrolyzer, which consists of an electrode, which is typically made up of iridium or platinum, an electrolyte solution where the electricity is going to supply. So when the electricity is applied to the electrode, the water molecule at the cathode side, which is at a negative uh, electrode, and reduces to form a hydrogen, while the water molecule at the anode side, which is on a positive one, are oxidized to produce the oxygen gas over here. So related to this, we required a gas separation. So hydrogen is going to be collected at the cathode side, while the oxygen is going to be collected at the anode side. So usually separated by a membrane or physically collected here. In terms of we are going to have the high purity content over here, and minimal contaminant. In terms of next process I'm going to talk about, that is the thermochemical conversion. Here we can see how it is going to be converted. So within this we have, yeah, so you can see this figure uh, where we are trying to understood this method associated with the thermochemical process. So thermochemical process encompass a variety of methods such as combustion, gasification, pyrolysis, hydrothermal liquefaction, but they all involve high temperature chemical reaction to release the hydrogen from the feedstock. So some simplified overview I'm going to give you. So first we start from the combustion gasification. So within this, the hydrogen production is a process that involves the conversion of an carbonious material such as the coal, biomass, or municipal solid waste into hydrogen rich gas, that is in form of syngas, that through combination of combustion and the gasification process. So the process involved, first, that is the combustion. So in the initial phase of combustion, a proportion of feedstock is going to be burned in the presence of oxygen to produce a high temperature heat, and this steps involves the high energy need for subsequent gasification. Next we have the gasification. After combustion, the remaining carbon rich residue undergoes gasification. During gasification, the carbonous material is going to be exposed to a high temperature in a limited oxygen environment, usually less than stoichiometric ratio. So the results in conversion of carbon into carbon monoxide and the hydrogen gas, along with other gas like carbon dioxide and the methane. Then cleanup process it is going to have. So the produced syngas contains the impurities such as tar, particulates, matter, sulfur compounds, and other contaminant. So gas cleanup process such as filtration, scrubbing,
Sorry
or
for interruption, sir.
yes.
Extremely sorry for interruption, sir. Could you please indicate the where are you explaining? Thoroughly, I am unable to catch up in the image
Here
which you are
that
displaying.
here
Laser pointer,
thermochemical.
please move laser pointer accordingly so that I can catch up.
Yeah, this portion, sir.
Okay, okay, sir.
You are going to try to focus on this. Ultimately, the content I am delivering, you able to catch it by means of this arrow part over here. Okay.
Right, sir.
Yeah. So gas cleaning over here. So where I have get left, I just so after this gas cleanup, we have the that utilization of syngas. After within this, the enriched hydrogen and carbon monoxide can be utilized in a various ways, where the feedstock associated with the chemical process, such as the production of synthetic fuel or chemical. Alternatively, a syngas can be produced for the power generation of the gas turbine and the combined heat and power system. So hydrogen is going to be separated from the syngas for a specific application associated with this. So within this, it is just like in a cycle where the combustion, gasification, where the char and heat we are going to have. So within this, the methanation and removal of carbon dioxide in order to have the biosyn over here. Then next we have the pyrolysis hydrogen production. So this is a thermochemical process that generates hydrogen from the organic material through a high temperature decomposition in the absence of hydrogen with a limited oxygen supply is there. So within this, some key points associated with the pyrolysis where the hydrogen production is taken. I'll going to explain that is the pyrolysis involve the subjecting organic feedstock such as the biomass, plastic or organic waste to a temperature of around 300 to 800 in a controlled environment to prevent combustion. And during this pyrolysis, the feedstocks undergoes thermal decomposition, leading to release of hydrogen gas as one of the primary product, along with the other gases like the carbon monoxide, methane, and volatile hydrocarbon. So based on this syngas formation we have. So gas produced during pyrolysis, we generally called it as a synthetic gas or a syngas, containing a mixture of gases including hydrogen. So the composition of syngas depends upon the feedstock, what type of feedstock we are going to have, and in the process condition. So some impurities or we are also going to have it. So syngas generated through pyrolysis, they contain significant amount of impurities such as tar, particulates or other contaminants. So which requires removal through cleanup process. So for that cleanup, hydrogen separation is going to be employed over here, and rich hydrogen syngas is further processed to a for the separation and concentrate the hydrogen. So technologies associated with this, that is the pressure swinging absorption or membrane one that can be used it over here. Then within this, we next we have this that is th- hydrothermal liquefaction. So within this, so within this hydrothermal liquefaction, that food waste and other feedstocks are going to be used over here. So it is an thermochemical process converts the wet biomass such as algae, sewage sludge or organic matter containing high water content. Therefore, it is mentioned, referred as a hydrothermal liquefaction. So containing high water content into a range of valuable product, including hydrogen gas. So related to the process associated with this, where the wet biomass is subjected to a high temperature and the pressure in presence of water, and the process takes in a closed reactor, preventing the escape of water vapor and the gases here, and where the reaction takes place at a high temperature and pressure condition. This reaction, the chemical reactions are complex, which includes the decomposition of organic material and reforming of molecule takes place. So the reaction leads to production of a mixture of an product, including the liquid bio oil, or gas product, including hydrogen and solid residue. So the hydrogen is going to be produced by here during the liquefaction process, and it produced through a decomposition of organic matter. So with water serve as a main source of hydrogen atom, and the hydrogen rich can be separate and collected for various application at different heights. Over here you can see. So the some other products we are going to have, that is beside hydrogen, this hydrothermal liquefaction can yield a liquid bio-oil that can further be processed for biofuel or chemical or solid residue, and they have a wide range of applications such as the biochar or other source of nutrient. So within this, we have the fractional distillation column over here, where at different heights we have the different byproducts we are going to have. Just like for a gasoline, jet fuel, or a diesel, at even the bottom, we are going to have the solid residue, which can be used or sell it to the small vendors. They are going to manufacture the paraffin wax, or this our in household we generally use that what we call naphthalene balls. So that type of this all carbon content, that residues we are going to have, which have a wide range of applications over here. Then next we have the biological hydrogen production. So this biological hydrogen production is split in two forms, that is the fermentation process and the biophotolysis. This process is further been all been splitted in two form other over here, that is the photo fermentation, dark fermentation, and this photosynthesis. We have the direct biophotolysis and indirect photosynthesis. So this biohydrogen production involves the microorganisms such as certain strains of bacteria or algae that produce hydrogen gas through metabolic process. So microorganisms specialized used such as the hydrogen products producing bacteria or algae over here, and they are this are microorganism acts as a feedstock to provide to provide over here, and the organic matter and the waste water containing the organic compound over here. So the metabolic process occurs over here, and during this microorganism metabolize the feedstock, and as a result they produce the hydrogen as a metabolic byproduct over here. So hydrogen harvesting we are going to have. So hydrogen can be harvested and collected by means of using this microorganism over here. So biological hydrogen production method is still in the research phase and development, and maybe have specified requirement for the temperature, pH, nutrient content, or optimizing the hydrogen production. So this the main working principle associated with the common hydrogen production, and each method have their advantages and disadvantages, making it suitable for different application scenarios. Even for, I'll just give you an example. that you have going to heard about that algae cultivation over here. Algae cultivation is also a one of the process through which this biological hydrogen production we can have. Even by means of algae, we can also going to produce a bio oil or algae based biofuel we can produce. One of my research scholar, that Aman Singh Rajput, have worked on this, and within our lab we have developed a biofuel associated with the algae. We have cultivated these algae in our lab, and we have the photo fermentation and dark fermentation, and uses some catalyst in order to enhance this process. And based on that process, we have collected the bio oil, and that characterization of that oil we have done it in IIT Indore and IIT Bhilai, and our results are very promising over here. And based on this, during I think in 11th of this 13 convocation, my research scholar get his PhD degree, and he got an gold medal in his best PhD thesis dissertation and interdisciplinary research over here, where we have generated this hydrogen production along with that biofuel, and we have used that biofuel to in the diesel engine to for having a carbon emission, in that how it is going to change it in near future in terms of carbon footprint and for sustainable mobility part of it. The next process we have the here, that is the photochemical water splitting. So within this figure you can see that how the hydrogen and oxygen is going to be generated by means of splitting the water over here. So for splitting the water, high temperature uh, uh, is going to be required, and the current is going to be supplied over here. So splitting the water, generally we use the sunlight to split the water into hydrogen and oxygen. So photochemical cells, that is which is in the heart of this process, so which consists of an semiconductor material as a photoanode or a counter electrode we can. So sunlight is going to be as acts as an observer. When the sunlight photon strikes the photoanode, which excites the electron within the semiconductor material and creating a electron hole pair, and the water splitting reaction initiates, where the existing electron can use the catalyzed water splitting to anode, where the uh, water molecule are oxidized to produce a oxygen gas. And simultaneously at the counter electrode, we are going to have the hydrogen production, where the reduction of a photon to form a water from the hydrogen. So gas separation we require, where the hydrogen and oxygens are going to be generated respectively. Electrodes are separate and the collected for the use. So this photochemical water splitting is an attractive method for a clean hydrogen production, although it faces challenges in terms of efficiency and the material development over here. Then next we have the high temperature water splitting. So within this, this is an this figure I have taken from Chu and Wong, where they have worked in the direction of development and synthesis of an fabrication process associated with the clean hydrogen production, where the splitting of water they are have. So the process including this, where the CO oxide and the solar radiation they are going to have. So in detail, I'll going to explain it out how they have worked. So high temperature water splitting involves the splitting of water at a high temperature using the ceramics and the metal oxide as a catalyst. So high temperature, first thing that is process is conducted at elevated temperature of around 1000 degrees centigrade. And the catalyst associated with this, that is the metal oxide, which is used to facilitate the reaction. Common catalysts include the cerium oxide or iron oxide over here. And water decomposition we are going to have. So at high temperature, the catalyst facilitates the decomposition of water into hydrogen and oxygen, and the oxygen is going to be released while the hydrogen is going to be collected at the another side. And the separation we are going to have for both this hydrogen and oxygen and collected for their respective application. So this high temperature water splitting is efficient but requires high energy input. So due to elevated temperature involved over here, so we can use some concentrated solar energy or a nuclear reactor to provide the necessary input energy over here in order to sustain the reaction over here. So this is one of the I think you may refer that required a huge economy or a huge infrastructure associated with this in order to sustain such type of process over here. Next, we have the hydrogen production from the biomass over here. So for this, we require the gasifier, reducer, oxidizer, combustor over here, and the working associated with this. I'm going to explain that how it is going to be work over here. So hydrogen is going to be produced from the biomass through various process. Just I have already informed, that is the gasification and reforming. So biomass is going to be used as a feedstock, which includes the organic material like wood, crop waste, residue, or home waste. You can also use for this. Where for this, the gasification and reforming we are going to have. So the biomass is subjected to reforming and gasification, and oftenly involve high temperature. Sometimes it introduction of steam we can have. So this process releases the hydrogen from the biomass and the gas sub cleaning. After this gasification, the hydrogen containing steam is cleaned up to remove impurity, and the purified hydrogen is collected for various applications. So hydrogen production from the biomass is a renewable and consider as a carbon neutral if the biomass is substantially sourced and managed over here. Then we have the next process, that is the hydrogen production from the nuclear power over here. So within this, first we are going to you can see this figure that requires a reactor, which, and within this reactor we have the cooling require, where the graphite core reactor, and this cooling that D2, that is heavy water we are generally going to use within this. And in order to harness the full potential of the hydrogen, this hydrogen production system can be parallelly been installed with the nuclear power system over here. So within this, nuclear reactor produces high temperature heat, and that can be used for high temperature electrolysis or thermochemical hydrogen production. So within the nuclear reactor, generated significant amount of heat during operation is at a very high temperature reactor. Here you can see it in figure, and helium coolant are generally going to be used. So this heat is going to be transferred to the high temperature electrolysis system or a thermochemical hydrogen production system, where the hydrogen is going to be produced by means of electrolysis, where the hydrogen and oxygen is going to be collected and using heat energy over here. And this thermochemical process, high temperature drives the chemical reaction to release hydrogen, and parallelly different separation tanks we are going to install in order to have the hydrogen and oxygen. So the hydrogen production from the nuclear power offers a advantage to continuous and reliable heat source, requires a specified infrastructure and safety consideration. So Therefore, it is considered as one of the best method to have a 24/7 hydrogen production, because generally in the nuclear reactor, we don't going to stop it suddenly over here. It is going to be operate 24/7, and based on that neutron and other production, these control rods are going to be used in order to control the chain reaction. So this nuclear reactor are generally going to be work 24/7, and based on this working, that how we can use the water for hydrogen production 24/7 over here. Next process is the hydrogen production from the solid oxide electrolysis cell. So hydrogen production from the solid oxide electrolysis is a clean and efficient method that utilizes the electricity to split the water into hydrogen and oxygen, and it is even it can be operate in a reverse mode also. It can be used as a fuel cell also. So this SOEC structure I'm going to talk about, that a solid oxide electrolysis cell consists of a solid electrolyte sandwich between the two electrode, anode and cathode. This solid electrolyte is typically made up of ceramic material, that is retrite stabilized zirconia. In short, we called it as a YSZ, and Scandia stabilized zirconia, SCSZ. It is generally been used, and during this electrolysis mode, an external power source, that is in electric energy, is in form of DC, we are going to supply to have the operation of this SOEC. And the electrical energy initiates to two separation, that is the electrochemical reaction at the anode side as well as the cathode side. At the anode we have the oxidation, and at the cathode we have the reduction reaction. Based on that gas separation, we have the gas is going to be collected at the hydrogen at the cathode side, while the oxygen at the anode side, and both gases are separated to avoid mixing. And in terms of purity level, I'm going to talk about this have the highest purity, and it is free from any contaminant or byproduct. So the oxygen which is going to be generated over here, it's also having a very high purity level, and they can be used for other industrial application over here. So the key advantages associated with the hydrogen production for SOEC includes the high energy efficiency, the potential of utilizing the renewable electrical sources, and the ability to provide the grid balancing by serving as a surplus electricity to produce hydrogen during the period of excess power generation. So this SOEC technology holds a promising for a clean and sustainable hydrogen production as a part of a broader strategy for green hydrogen generation. And the choice of hydrogen production method depends upon the factor, just like what type of feedstock we are going to have it, or in terms of availability, energy source, or cost consideration, and the environmental goal. So as the demand of hydrogen grows, the renewable energy becomes a most prevalent, and this growing emphasis on the production where the green hydrogen through a method like electrolysis or a biomass conversion to reduce the carbon emission associated with this. So within this we have that cover the production part, and now we have the storage part over here. So within this storage part, first we start with this processes, that is the physical based or a material based, how we are going to store. So this physical based has been categorized in three forms. That is, first we have the compressed gas, then we have the cold cryo compressed, then liquid hydrogen. Whereas the material based, we have the absorbent process, then liquid organic, then interstitial hydride, complex hydride, and chemical hydrogen over here. So these are the main categories associated with this. So first we start with the physical based one, that is the compressed hydrogen gas. So in this method, the hydrogen is physically compressed at a high pressure into storage tank. The working principle is just a straightforward. The energy is stored for packaging the hydrogen molecule close together under pressure when needed, and a high pressure hydrogen is going to be released for various application, such as for fueling the vehicle or fuel cell technology for the vehicle or mobility purpose. Then second we have the cold cryo compressed hydrogen. So this is a hybrid method. So hydrogen gas is first cooled to a cryogenic temperature and then compressed. So cryogenic temperature in terms of minus we are going to have, and the working principle combines the benefit of both cryogenic storage as well as the compression. So cooling the gas reduces its volume, making it easier to compress and store at a high temperature. So this approach provides an efficient way to store the hydrogen at high density for various applications. And in third, I'm going to talk about that here. This is the cryogen compress. Here you can see the schematic diagram where this compressed hydrogen gas and the cold cryogenics are going to be mounted, where the coaxial tubes we are going to have, which is made up of carbon fiber and which can resist high pressure vessel, and a composite support rings are going to be mounted across, so that the vacuum shells, which are made up of stainless steel, and this hydrogen is still going to be filled over here, and here based on this liquid hydrogen filling line we are going. Here in the compressed one, which is made up of carbon fiber composite and high poly density polymer in liner we are going to have, in order to maintain the safety concern, and the dome protection along we are going to have it. So the ball and the bosses, so along with the temperature sensor is parallelly going to be mounted, and based on this the compressed hydrogen gas we are going to have. Next we have this liquid hydrogen. Within this liquid hydrogen, this you can see that how it is going to be done. So how this inner vessel, outer vessel, and parallelly hydrogen cold box, and so this liquid hydrogen, which is work on the cryogenic part over here, that is cryogenic liquid. So hydrogen is going to be cooled to an extreme low temperature, that is minus 250 degrees centigrade, and to become a liquid. And the working principle involves the storing the hydrogen in a liquid stage, where it is occupies the significantly less volume compared to gaseous state, and thus achieving high energy density when needed. And the liquid is going to be vaporized and used, typically used for the rocket propulsion or a fuel cell based application over here. So this liquid hydrogen process is one of the most commonly used method for the propulsion of rockets and other things. So where these liquid hydrogen are going to be supplied. Then next we have the material based hydrogen storage we are going to have. So first we have the absorbent method. So within that absorbent method, we generally employ the metal organic framework or a metallic foam we can have it. So within this, we have made up of different hybrid methods over here, where the doping we are going to generally done, and based on this the hydrogen is going to be absorbed over here. And related to absorption,
सारा टीचर प्रोफाइल कंप्लीट है आपका ये मैंने
so it is made up of porous material, which is having an activated carbon, and or a metal organic framework, that is in short we can call it of MOF, are used in this, and involves the absorption, where the hydrogen gas molecules are physically at, attract to or held on a surface of a porous material, and when hydrogen is needed, this gases is released by reducing the pressure or increasing the temperature, breaking the physical bond between the hydrogen and the absorbent material over here. Then next we have the liquid hydrogen uh, liquid organic hydrogen carrier. In short, we called it as LOHC. LOHC are the organic compound that reversibly absorb or release hydrogen through catalytic reaction. And its working principle involves the central chemical bonding, and the hydrogen is chemically bonded to the LOHC material when storing, and release process involves the breaking of this chemical bond under the specific condition, such as the aid of some by means of some catalyst over here. Then another method, we have the interstitial hydride method, and within this we generally use the precious metals, just like the nickel or lanthanum side over here, where you can see this green one and the blue one represents the hydrogen, that how it is going to be absorbed in terms of molecule level we can see. And related to this principle, I'm going to explain that how. And parallelly we also going to have the complex hydride. So the main method associated with this, we can discuss it over here. Wait a minute. I'm trying to animate this. Wait a minute. My screen is visible.
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir. Yes, sir.
To animate it, uh, I think some problem is there with media player over here. So let me explain it how it is going to be work. So here that certain metals like the palladium or lanthanum can absorb the hydrogen atom into this interstitial sites of their crystal lattice, and the principal releases for the formation of metal hydride, where the hydrogen atoms are integrated into metal atomic structure. To release this hydrogen, absorb hydrogen, these metal hydrides are going to be heated and exposed to a low pressure, causing the hydrogen atom to deabsorb from this metal lattice. So this process involves the absorption of hydrogen to a lattice structure over here. Then next we have the complex hydride. The compounds like sodium borohydride, that is in short we called it as a NaBH4, contains the hydrogen combined with other element. So it involves the chemical reaction where the hydrogen is either released or absorbed from that compound under specific conditions. So catalyst and the temperature changes and facilitates this reaction over here. So within this, we have the chemical hydrogen storage also. The hydrogen is going to be stored in a chemical compound in form of ammonia, and its working principle hinges a reversible chemical reaction that is going to be allowed. And based on this this nanoparticle and catalyst, we are going to use it over here. And this is one of the most significant method, and generally still it is in a deployment stage, where how it is going to be used for industrial and other application. So this, since the ammonia is inflammable, and this handling part is very difficult associated with this. So some researchers are still work on this method, that how we are going to have this chemical hydrogen storage related to ammonia part. So here we have completed this part, and we may have the query associated with this. Storage portion we have covered, and related to this we can have the questionnaire.
Does anyone have any questions?
Good evening, sir. This is Dr. Suresh Chand from Punjab Union College, Chandigarh.
Yes, Professor Suresh, yes.
Sir, first of all, thank you very much to give a nice presentation. Very carefully you explained that storage part and that production part, and it is very clear.
uh,
So, thank you so much, sir. One thing I want to know, sir, just then in the metal hydride case, whether some materials already developed in our country or in any country that are deployed yet or not, or still it is
uh,
in nascent stage.
Related to this portion, in CSR Ampri Bhopal, they are working in the material aspect. So they are trying to developing or trying in the direction of synthesizing associated with this. One of the related to material aspect, I'm going to have that IIT Bombay, and along with the collaboration of one of their lab of CSR. I didn't able to recall. I have recently visited ASME conference in Hyderabad recently in the September part. Over there, one of their private player and IIT Bombay to collab over here, and they have shown the showcase the this material or hydride, but they didn't show that what type of metal or that thing they have used it over here in their hydride, but they have synthesized it. And even in the IIT Tirupati, Professor P. Muthu Kumar is working in this direction, and they have developed the metal hydrides in their lab, and they have also tested and produces various PhD scholars who have worked in that this direction.
Thank you so much, sir. I would like to request you, if possible, please provide your PPT. It is very much informative and it can help us to direct ourselves.
Okay, okay, I'll try to share it.
Thank you, sir.
Any other questions?
Um, uh,
Sir, one question from my side, sir. Can
yeah,
I?
yeah. Please, please. I
Sir,
love to.
one thing you have mentioned in a storage of hydrogen, like about a cryogenic technique, sir. Sir, as an assistant professor, also I worked on cryogenic technique in our university in aeronautical engineering department. Sir, the question is that the for storage of hydrogen, cryogenic fuel at a very such a low temperature at a minus 253
253 degree
degree
centigrade.
centigrade, to maintaining this temperature, we don't you think that we need such a high insulating device, and for maintaining this
Yeah, yeah, yeah. For
very
that,
difficult.
infrastructure part is very important over here. To attain that temperature, for that itself, we required a huge energy input over there also. If you are go for the techno-economic analysis in terms of what type of input you are going to give it over there, and how much the hydrogen you are going to extract it from that. So it's little bit quite challenging to that in terms of that. अगर समझने कोशिश करिए कि उस प्रेशर टेम्परेचर के लिए आपने मान के चलिए कि 100 रुपीज आपने वहां पे इन्वेस्ट किया, एक शॉर्ट एग्जांपल मैं दे रहा हूँ, और उसी चीज को आपने जो उससे हाइड्रोजन प्रोड्यूस किया, वो क्या वर्थेबल है 100 रुपीज के कि उसके ज्यादा के लिए? सो इट्स लाइक एन डिबेटेबल थिंग ओवर हियर. Related to this, the research are still going on in the area of cryogenic part, that for that requires a huge infrastructure to attain such type of temperature and pressure for that part. Once we are going to have that thing, ultimately the production part not so big challenge over here. Main thing over here that is infrastructure and the cost associated with this. So in my next presentation, I'm going to cover that part also, that how that infrastructure development is going to be taken up and related to the techno-economic aspect, and what are the things in India, that how this hydrogen is going to be taken up by means of national hydrogen mission. And even I have also contributed in that perspective, that how that my work is also been recognized by the Ministry of Education, where how this I have put up a small contribution in terms of promoting this hydrogen national hydrogen mission to a next level in the direction of indigenization of hydrogen engine within the India part over here.
Right, sir. Is
So
there any other questions?
next session at around 7:30, right?
Right, sir.
Okay, okay. May we have other questions over here, participants we have?
Yeah. Can
Even
you explain
over here.
hydrogen storage through physisorption?
Yeah, sorry, pardon, please, sir.
Hydrogen absorption through hydrogen storage in solid materials through physisorption. Actually, this is a very promising field
Yeah,
now.
yeah, that part is also absorption and data process is very, but the releasing part, that how we are going to release once it is going to be absorbed, and after that how we are going to release back it. That process is little bit challenging over here. That related to conversion part, if you are going to talk about in terms of efficiency, that how much absorption that it will going to have, that same amount it should going to have it in another part, so that thing is not going to be practically being attained in that much level of efficiency. So some noble catalyst be required for that part, so that the absorption in terms of lattice, I'll just shown that how it is going to be taken up, that absorbing the hydrogen in terms of lattice part and how it is going to be released. So that thing, it is still in the research phase, but the results are what whosoever the scientists they have carried out in terms of that, they have got the marginal efficiency in terms of absorption as well as the desorption of the hydrogen over here.
No, I am talking about adsorption. That is through van der Waals forces, not absorption. So that is you require very little energy to release the hydrogen also. Adsorption through
Okay,
van der Waals
absorption you
forces.
are
So
talking
you
about.
can have multiple layers on the single metal
Yeah, yeah, yeah.
ion.
Multiple
Yeah.
layers we are going to have there based on that, and based on that layer to layer, we have the desorption process over here.
Right. So that part perhaps you can explain because it was not covered there.
And
If you
actually,
have
I
time,
have
yeah.
just covered in the level of, so that what are the different techniques we are having right now in the phase. Right now, in terms of, I'll talk about the graduate or postgraduate level. These contents are not in that context to have to get the knowledge. It is still in the
Oh,
research part, and you can have it through by means of research paper or some special calls of books over here. So that part you can have it, but these
okay.
things may be introduced in the syllabus part also, or maybe offered in terms of elective, so it will very going to be the informative part also.
Yeah, actually, because in a very short space, you can have high dense storage in this, and not much pressure or not much
Yeah, yeah,
energy is also required.
yeah, yeah, yes, sir.
Okay, thank you.
Is there any other questions from any one of your participant regarding the PPTs?
So we can have a 5 minutes break over here, then immediately we can start our session
Yes,
over.
sir. You can take a break, sir. From
Okay,
7:30 onwards, we can carry on from the next lecture.
sure, 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 sure.
Okay, so
Okay.
sir,
First of all, I just apology that from my end that animation is not working properly due to having some technical glitch over here. So I completely apologize for that part from my end.
No issue, sir. No issue.
Okay, okay.
Okay,
So I
so
we are going to meet at
7:30.
5 to 10 minutes break, and
Sure,
we
sir.
are going to start the session. Okay,
So
okay.
here we can conclude the session, and we are sincerely gratitude to our respected resource person, Dr. Tushar Chaudhary, sir. We are sincerely greeting for this engaging presentation and have a greatly enriched session to all the participants have been participated in this faculty development program. We are highly obliged to the Dr. Tushar Chaudhary, sir. Also, one thing I should have to in add up in this session that the feedback link has been shared up in the chat session. So kindly put up your feedback through this link. Also, one thing I have to request to all the participants, kindly switch on your camera so that we take a proper screenshot of this session.
So, sir, this within this FDP, the whole faculty from your institute or around that India, across India?
Across India, sir.
Okay, okay, okay. It's a great pleasure to interact with all of you, even the senior colleagues over here. I feel little bit younger over here. I'm just a 34 over here, sir.
There are a lot of faculties from different states and different institute across the nation, and we are so obliged that this topic has been a futuristic technology in which we cover the green hydrogen and future of renewable system. So we are also thankful to you, sir, for involving in this session and giving your valuable time for the futuristic technology. And I hope so that your session is going to be very beneficial, informative for the whole of the faculty members has been involving in this faculty development program. Thank you,
Sure,
sir.
sure, sure, sir.
So
So
you can take a
within
break, sir.
5 to 10 minutes break, we
Sure,
can
sir. You can
continue
take a
our
break,
session.
sir. Sure.
Yeah, yeah. Okay.
So guys, the feedback link has been shared up in the chat section. You can go through it. Also, the screenshot has been taken up, and we will meet up in our next section from 7:30 onwards. Thank you so much for continuously you are in this faculty development program and continuously be up with the session from starting. So next we will meet up at 7:30 with a next session.
Yes, Maharaj. Kamalya. Kamalya. And Kamalya.
Hello, sir. I am audible.
जी सर.
My screen is visible.
No sir, not yet sir.
Okay, okay. Wait a minute. Now it is visible.
आ गई सर.
It is visible.
Yes sir, yes sir. हाँ आ रही स्क्रीन.
Yes, sir, it is visible.
Okay sir.
So shall we start, sir?
एक थाली का
Wait, sir. Let's.
दाल चावल छोले की सब्जी पुलाव जो तो दे दो
Am I audible to everyone?
चावल बढ़ा के रखना
Yeah, you are audible, sir.
सबका नाम लेना और दो साल बैठे हो तो
Once again, I would like to request to all the participants kindly join the session. And the next session has been going to start it very soon. I would like to request to all the participants kindly join the session.
Sir, you just stop my sharing. I once again I'll just share my screen. Actually, here some problem is.
Sure, sir, sure.
Stop sharing option is not coming over here from my end.
Now just see, sir.
Now my screen is visible.
No, sir. Kindly log out, then again.
Okay. Just I make sure that I wait a minute. Wait a minute. I just log it out and again once log in.
Sure, sir. As sir is joining the session now, till then I would like to request to all the participants kindly join the session. So your next session has to be started very soon. Is that okay, sir?
Wait a minute. Now my screen is visible.
No, sir.
Video is there. Slide is not there.
Slide is not present here, sir.
Is it visible?
No, sir.
Slide is not visible, sir.
Yeah, I'm trying to share it, but here some issue is going on. Now is it visible?
Yes, sir, you are visible, sir.
Yeah, thank you. So, shall we start the session?
Okay, sir.
Sure, sir.
Okay. So,
Slide is not visible.
good evening, all of you. So today I'm going to speak about the hydrogen infrastructure development, which is a critical enabler for the transition from a conventional fossil fuel based system
Wait,
to a low hydrogen net zero energy future. Hydrogen is well known is not just another fuel; it is an energy carrier that connects renewable generation, storage, transportation, and end use sector. So this lecture is exclusively focused not only on the hydrogen production technology, but more importantly on the infrastructure ecosystem required to make the hydrogen deployable at a scale or covering the production, storage, transportation, distribution, safety, even the digitalization and the policy framework we are going to cover. So the discussion is going to be aligned with the global effort and the India's national hydrogen mission and emphasizing the real world deployment rather than the laboratory concept. So here we have the learning objectives that based on that you are going to get it. So within this we are going to cover the hydrogen infrastructure associated with this, and based on this that how it is going to change the
Excuse me,
scenario.
sir.
And
Share screen, sir.
wait a minute.
I could see you, but I could not see screen.
Now it is visible.
no, sir, no.
No, sir.
Sir.
Previously it was visible.
So slides
Screen
of
is
the
not
PPT
visible,
is
sir.
not visible, sir.
Yes, the previous one was visible.
Sir, is it possible to you can share the slides with
Yeah,
us?
yeah, yeah.
Okay.
I'll share your PPT. Please operate from
We
your.
can we can share the slides from here.
Yeah, yeah, sure. That will be okay, I think.
इसको भी जाओ। उसमें कर देंगे।
I have shared this screen that PPT with you. Please open it. Please open it and share it so that I can tell you when it is about to change it slide by slide. Okay, that will be okay. Some sharing options has been changed. I think I have right now checking it over. The Zoom.
Sure, no issue, sir. We can operate it from host end.
Okay, okay.
If
That
you
will
can
be.
if you can share your slides with us,
Yeah, I've already shared. I checked your WhatsApp. I've already.
sure, sir. Sure, sir. Sure.
इनको host बनाओ जरा सचिन बना सके।
Please check it out. I am sharing the
Sure,
WhatsApp.
sure, sir.
Host
Host or post?
आपको host।
Okay, sir. Now visible.
Now it is visible.
Yeah,
Yes,
yeah,
sir.
now it is visible. Go in presenter mode over here.
This is just a technology, and due to this technical glitch, we are
Just go to
really
in
sorry
second
for it.
slide where I'm talking about the learning objective.
Sure, sir, sure.
Yeah, yeah, great. So by yeah, this one. Uh, Go to in second slide. Yeah, this one. Great. So by means of this session, we are going to have the learning objective over here. That within this, first we are going to understand what is the hydrogen infrastructure and its value chain. Identify the key technologies associated with the hydrogen production, storage, and transport. Then analysis the hydrogen role in renewable integration and grid support, recognize the major techniques, safety and economic challenges associated with this. And at last, we are going to have the related to hydrogen infrastructure, net zero, and national energy mission we are going to talk about. So this is a brief outline of learning objective. So by end of this session, you are able to understand the complete hydrogen infrastructure value chain, identify the technology across the production, storage, and analyze the role of hydrogen. So you should also able to recognize the major techniques, safety, and economic challenges that currently limited hydrogen deployment we are going to have it. And finally, the hydrogen infrastructure development to a global net zero and national initiatives, just like an national hydrogen mission, we are going to have. So this objective will going to guide the structure of this session. So we may going to proceed. So please change the slide. Just little bit one more some animation will going to have. Just put एक बार और press करिए. Yeah, concept we are going to have. Yeah, so within this just one more time. One more time. Yeah, one more before going to next slide, just like this. Yeah, yeah, actually yeah, this one. Okay, so actually I have put an animation over here, so related to get a more clarity about this. So related to this hydrogen infrastructure, that concept of this, where the hydrogen infrastructure enabling the hydrogen economy. So hydrogen infrastructure represents the physical as well as the digital ecosystem required to enable the hydrogen as a mainstream energy carrier, planning for the production from end use. So this is the basic definition. We are going to expand it here in terms of hydrogen infrastructure, which is the multi-layer consisting of an economic system of physical assets where the plant, pipelines, tanks, you can have it here from this figure over here, where the hydrogen production, industrial applications, supply and distribution, networking we are going to have. Then in terms of digital assets, we are going to talk about that how it is going to be control, monitor, and forecasting. And based on the regulatory and the safety framework, if we are going to talk about, that part is very important, because based upon the market and logistic network we are going to have it. So here the hydrogen infrastructure having the main complete physical and digital requires the enabling the hydrogen to a mainstream energy carrier over here, from energy to feedstock to hydrogen production, hydrogen packaging, and transportation. Then after transportation, hydrogen unpackaging and storage. And at lastly, we are going to have the hydrogen usage, whether it in form of heating, power generation, mobility, transport, co-generation, and in the industry over here. So therefore, hydrogen is not a fuel problem alone. It is an infrastructure challenge over here. So many hydrogen technologies already exist, but without coordinating infrastructure, hydrogen cannot move from production site to an end user safely, efficiently, and economically over here. Next slide. Yeah, little bit. Yeah, so here we are going to discuss about the hydrogen imperative. Why now? So here, yeah. So here the key drivers we are going to have that it will going to uh, dear admin, please unmute other participants. I think some mics are on over here. Yeah, thank you. So related to hydrogen imperative, we are talking about that urgency of hydrogen infrastructure arises the several converging drivers over here. Firstly, the hydrogen enables the decarbonization of hard to abate sectors, just like in steel, cement, or heavy transport or chemical areas where the direct electrification is very difficult over here. Secondly, the hydrogen provides a long duration and seasonal energy storage, solving one of the biggest challenges associated with the renewable energy. And thirdly, we have the improved energy security by reducing the dependence on the dependence on the imported fossil fuel and minimizing the renewable energy curtailment over here. So at a system level, hydrogen effectively acts as an chemical battery over here for the grid and enables the sector coupling between the power, transport, and industry over here. So if you are going to see this picture over here where the sectors are going to be coupled and in form of integrated energy system based on the renewable energy. So how it is going to be connected in terms of power to mobility, power to gas, or power to heat for various application. For power to mobility, we are going to talk about by means of the here you can see where in terms of electricity by means of renewable energy, solar and wind, it is going to be integrated. And in terms of gas to power, it can be used for again for mobility. So in two way it can be integrated. And another in terms of power to heat for heat of heating the building and industry part as a fuel, we are going to have it. And based on this, they have the key drivers for the industry, transport, and power. You can see it from here. And in terms of global demand projection, if you are going to talk about as per the agency, International Agency of Energy Agency report over here, IEA 2023, it will going to have it in terms of more that by 2020 90 megaton, then 2030 ton, and at 2050 it will going to rose to 660 megaton over here. So here how the networking associated with the power, that how the energy renewable energy is going to be coupled over here. So at this bottom side one figure you can see how this networking is going to be connected, so that how hydrogen flow and electricity flow lines are going to be interlinked with each other and form a networking of an coupling each sector by sector, from power sector to household or electronic industry, chemical industries, how they are going to interact with the transportation networks. All are going to be been a part of this ecosystem we are going to have it over here. So this is an hydrogen production, um, that is hydrogen imperative here. Why now over here we are going to how it's deeply going to be harder to abate the different sectors over here. So please change the slide. Now we are discussing about the hydrogen production infrastructure associated over here. So within this, that first we have to know that hydrogen value change from the production line to end use. So the value chain has been shown over here, where the production, processing, transport, storage, and end uses has been shown over here. So within this hydrogen production infrastructure, particularly the green hydrogen pathway. So the green hydrogen is produced through water electrolysis using renewable electricity. There are three main electrolyzer technologies associated over here. That is the alkaline, alkaline, then PEM, that is the polymer electrolyte membrane, then AME, that alkaline membrane technology, AME and PM. Each have distinct characteristics in terms of cost, response, and scalability. And in terms of cost and technological matureness, I'm going to talk about that alkaline one is quite mature. Then PEM is fast response and it's having a compact structure. And in terms of EM, I'm talking about that anode membrane. This is one of the emerging and low catalyst cost process over here, and so they are categorized in such a way that cost, response, and scalability is very important over here. So beyond this electrolyzer itself, the production infrastructure includes also that elements required the infrastructure element, just like the solar or wind farm or power conditioning unit, water treatment and balance of plant, hydrogen purification. Oftenly, the balance of plant accounts for the significant shares of total system cost, making the infrastructure design as important as an electrolyzer stake over here. So some supporting infrastructure is also going to be required in terms of deionized continuous supply over here with an a magnitude of 9 to 10 liters per kg, so that hydrogen can be generated for even the power electronics, just like in AC and DC rectifier, cooling, thermal management, hydrogen purification. So here with this, all this plays a very important role in the hydrogen value chain from production to end use over here. Because ultimately, from the first part, ultimately the end users were going to contribute a major share by means of industry, which is going to have a capture of 55%, then 30% for the transportation part, and rest remaining for the power and other user over here. So here, this is a hydrogen value chain, which is give a glimpse of an hydrogen production infrastructure over here. Next slide, please. Then we have the production scalability and the location strategy over here. So within this, first we have the hydrogen production must be strategically located. So centralized production involves the gigawatt scale plant aimed to export or industrial supply and requires pipelines or a shipping infrastructure over here. So in contrast, I'm going to talk about that decentralized production uses the distributed electrolyzer located near consumption points such as EV stations or industrial clusters over here. So that thing we can have it. You can have it seen over here in form of figure over here, that decentralized standalone system, how the hydrogen can be used directly from the renewable by means of electrolysis and directly shipped to the consumer in terms of mobility part. Where the another figure where the decentralized by means of grid connected, the electricity is going to be taken up by the grid, and here at last we have the centralized one, where from the grid it is going to be have, then LRC, then we go for the storage part in terms of then transportation, and at last to the station part. So the key location factors includes the renewable source availability, water access, land footprint, grid congestion, and proximity to port. For example, desert solar region favors green hydrogen hub, while the coastal wind region are ideal for green ammonia production over here. So they have different strategies over here. You can see it from here, location wise. If you are going to talk about, this is a US figure where the Pacific West is hydrogen hub, California hydrogen hub, Heartland hydrogen hub. There are different locations they have make it, which is going to be proposed the facility, hydrogen facility, and some selected H2 hubs over here. So how it is going to be transported? This is on a US base, and if you are going to talk about at the bottom one, where how much the cost of hydrogen delivery will going to have it in terms of current and future. So if you are going to see the trend, the cost of electricity is going to be reduced over here, and ultimately in the hydrogen transport portion, that will going to be increased over here for different purposes. That is for the decentralized one or for the centralized one, as well as for the decentralized to grid one. So here we have the cost of hydrogen delivery comparison over here by means of this graph over here. You can see it over here. So in the future part, all of this cost will ultimately going to be reduced over here, and this will going to be the game changer technology in the upcoming future over. So for that, some sustainable technology associated with this, we have to make it in a deployable so that this technology can be sustainably be adapted to each and every community over. So this is the production scalability and the location strategy over here. Next, we have the please change the slide. Yeah, here. Yeah, the previous one. Yeah, you can see how the comparison matrix has been shown, that centralized and distributed over here in terms of cost. So the centralized one is going to be little bit cheaper around. This all these figures are in the dollar part. You can see from here, and the location wise, the centralized one is going to be have a different variation, whereas in case of distributed one, the refueling stations and industrial sites we are required. So infrastructure needs over here, that is the large power connection, water supply and export facility. Whereas in the distributed part, grid connection and limited space is required. So if you are going to have it in the geographical distribution, the key renewable and nuclear hub over here. So you can see it all over the globe. I'm talking about all over the globe over here. The wind hubs is widely been spreaded over here. Then after it's came to United region over here, nuclear is also there, but you can see it very little over here, and the solar farms over here. So this is the existing one, and based upon that location part, this the energy market and the matrix comparison has been made over here. So hydrogen infrastructure has a huge capability to interact or integrate with the other systems over here. So please change the slide so that that thing we are going to have. Uh, please change the slide. Yeah. So hydrogen storage infrastructure are going to talk about. So for this, the storage methods here. So hydrogen storage is one of the most critical and challenging component of the infrastructure over here. So hydrogen has a low volumetric density over here. So meaning means storing the dominant both cost and safety consideration over here. And the storage option includes the compressed gas, liquid hydrogen, solid state material, each such as the metal hydrides or MOF, chemical carriers like ammonia, LOHC. Each option involves the trade-off between the energy density, efficiency, cost, safety, and making storage selection application specific over here. So related to this, that how it is going to be stored, I have already been stored. Explain that different why and how the process is going to be defined in the molecular level. So based on this operating things, that how to reach that attain that type of temperature, pressure, or gaining the extraction of precious metal for this, all these things are falls under the category of infrastructure, which is a quite challenging over here. So hydrogen needs to be have a has a low volumetric energy density. So storage dominates the cost and safety consideration over. So please change the slide. So related to comparison of storage option, if we are going to talk about that, here we can see, yeah, comparison has been made it over here. You can see that different storage type, that compressed hydrogen, liquid hydrogen, metal hydride, in terms of energy is also having. So within this, the ammonia and LOC has the highest energy density, and the lowest one we have the compressed hydrogen. In terms of cost, we are going to talk about medium. We are going to have the this one compressed hydrogen, and the highest one we have the liquid hydrogen and the metal hydride. So and in terms of safety over here, compressed one have the moderate, liquid hydrogen have the lowest, and the metal hydride and LOC has the highest. In terms of technological maturity level, if you are going to talk about this LOHC and the ammonia, the metal hydrides both are in the emerging phase, and they have huge potential in the near future. So hydrogen storage comparison, if you are going to talk about in terms of duration and the cost over here, you can see it from the chart over here, that how much it will going to have, and the season wise on range wise it will going to have, and the cost wise also. So storing the where, yeah, that hydrogen in our LHC or in ammonia form is one of the high, medium one, whereas in case of liquid hydrogen and this metal hydrides, they have the huge costing over here. So that thing we are going to have. But in terms of longer duration, if you are going to have, we have underwater, underground salt caravans over here, where it can be stored for most of the duration times over here. So even the in terms of storage part over here also. So that thing we are going to cover over here. And this time, if you are going to talk about the geographical storage potential region, in North America, 450 terawatt hour of that production we are going to have, whereas in the case of Europe specific, 150 terawatt hour, and in the Middle East we have the 380 terawatt hours over here. So this is the storage potential around the region over here. Next slide, please. So here, if you are going to talk about the transportation network over here, so hydrogen highways, that is the hydrogen highway within this. So once the produced and stored hydrogen must be transported. Transportation option includes the depicted pipelines blending hydrogen, natural gas pipeline, tube, trailer, liquid hydrogen tankers, and ammonia shipping also fall under this one. However, the hydrogen transport presents the engineering challenges such as the hydrogen embrittlement, leakage, or material compatibility. So these challenges are going to solve. Challenges necessitates the advanced alloy and the polymer inlining, continuous monitoring, and strengthening the safety protocol, making the transport infrastructure as a key research and an investment area over here. So we can see it in terms of energy efficiency and the cost over here, that once we are going to attain the maximum efficiency, ultimately the cost will going to be reduced it over here. Even in terms of pipeline or tankers or tube, if we are going to talk about, the range will also going to be decreased it over here. So efficiency in terms of how much the gases we are going to have, the cost will going to have. So the lesser will be the cost in terms of transportation and other. So we have to keep in mind that energy, this engineering challenges we have to taken up, and once we are going to resolve these challenges, ultimately the cost will going to be reduced to much level over. Next slide, please. Here, underground and large scale storage we are going to talk about. Here you can see a salt caravans over here. So for a grid scale and seasonal storage, underground storage, particularly this salt, uh, plays a vital role. This caravans allows a massive hydrogen quantity to be stored in a very low leakage rates over here, and this is one of the world's first highest impurity commercial caravans. You can have it over here. So such storage enables the renewable energy to function as a base load resource and provide a strategic energy reserve and enhancing the national energy security over. So countries within the suitable geology are readily investing heavily in this type of infrastructure over. So strategic improvement is going to be required, so enabling the renewable base load equivalence over. So you can see it here from the figure that how this caravans, that salt caravans are being shaped in the crust over here, and within this the storage is going to be taken place. Next slide, please. Yeah, related to this hydrogen distribution and refueling station. Hydrogen distribution is the most viable through hydrogen refueling station. In short, we called it as a HRS. This station includes a compression unit, buffer storage, pre-cooling system, and the dispenser over here. And typically, dispensing pressures are in the range of 350 bar for buses and trucks and 700 bar for the passenger vehicles. Stations may be used on-site electrolysis delivery hydrogen for or for hybrid configuration combining the battery and hydrogen. So standards such as SAE J2601 govern the refueling protocol to ensure the safety and the consistency over here. So related to this, you can see it here that for refueling, if around the full time, if you're going to have 3 to 5 minutes, it's going to take place, and the dispenser capacity is going to have that 60 to 180 kg per hour over. So for that equipment, if you go for the um, cost breakdown over here, typically for 1000 kg per day station, the equipment carries around 65%, and commissioning this they have defined civil work 20%, field work installation 10%. So in this way, we are going to have it. Please change the slide. So this is a hydrogen refueling station architecture over here. So related to the commissioning, installation, civil and equipment, and how much time it will going to take place. It will going to. Please change the slide. Yeah. Next one, we have the hydrogen infrastructure for mobility. So hydrogen infrastructure enables the uh, fuel cell electric vehicle across the multi-segment, just for car, buses, trucks, rail, and even in the defense mobility over here. The main advantages include the fast refueling, longer drive range, zero tailpipe emission. However, the mobility application requires ultra high hydrogen production purity over here, typically around 99.9999%, and the refueling time of less than 5 minutes it will going to require. So real world example, it will going to have their Toyota Mirai, which is a vehicle developed by a Toyota. And currently in India, our Honorable Transport Minister, Dr. Nitin Gadkari, is having that Toyota Mirai vehicle. It is also offered flex fuel option also, that it can be run by any fuel also. And the hydrogen buses already been deployed and still in the testing phase in the Europe and India over here. And within the India, that Tata Motors have taken the initiative and they have showcased their hydrogen bus over here within the. And soon it will going to be go for the commission, and it will going to be commercialized. So if you are going to talk about the hydrogen fuel cell architecture over here, you can see from this figure, it consists of a fuel cell stack, electric traction motor, DC converter over here, thermal system for cooling of the battery, then transmission, then power, electronic control, and auxiliary for battery pack. And lastly, we have the fuel tank, which is an cryogenic tank which can store the hydrogen where the fuel filling is. And over there, another battery pack is going to be installed over there. So this is an architecture of an hydrogen fuel cell electric vehicle over here. Next slide. Please change the slide. No, no, no. Next slide. Your previous slide you are taking. Next slide. Next. This is the previous one. Yeah, this one. So here, hydrogen infrastructure pathway, if we are going to talk about. Yeah. So this shows the hydrogen infrastructure development pathway. So it will going to be achieved by year, by phase wise. We have to work it out. So phase wise development of hydrogen infrastructure for localized system to fully integrated global network to a period of 2020 to 2050 we can have. So within the first phase, that is in 2020 to 2030, hydrogen infrastructure emerges in Island hubs where the centered around the industry cluster that acts as an anchor demand, and hydrogen is going to be produced and consumed locally, primarily using the renewable power electrolyzer. Uh, with a very limited transportation, typically within the 50 kilometers. And this phase focused on the cost reduction, technological validation, and pilot scale deployment requiring the relative moderate investment of around 100 to 200 billion dollars. In the next phase, where this is an isolated hub, begin to interconnect forming regional hydrogen network, where the medium distance hydrogen transport is in the range of 50 to 500 kilometer become feasible through dedicated pipelines and rail or road network. And initially backbone The pipeline system or network are developed to link the industrial zone, port, or emerging mobility and the power sector application. So this emphasizes the phase shift towards the large-scale deployment and infrastructure standardization and the market expansion. So with the investment, initial estimated investment of increasing around 500 to 800 billion dollar. And lastly, in the third phase, that is 2040 to 2050, hydrogen infrastructure involves a national and global hydrogen grid comparable to today's electricity and natural gas network. This phase is characterized by fully integrated infrastructure, long distance and international hydrogen transport through transitional pipelines, shipping of liquid hydrogen or ammonia, and the use of multi large scale storage options such as the underground caravans, chemical carriers. So, by means of this, we can attain. So, the primary focus on the market integration, optimization, and cross-border energy trade. So, with total investment reaches to around 2 to 4 trillion dollar over. So, overall, this figure highlights the hydrogen infrastructure development is gradual stage process, and where the every technological learning and the cost reduction enables the regional scaling, ultimately leading to a global interconnect hydrogen economy over. So we can attain this by phase. So it requires a huge research and development investment in each and everything. So one day it cannot be attained. So phase wise we have to work it out for the development part. Please change the slide. Yeah, here. Next slide is the power sector integration. So, hydrogen also integrates deeply with the power sector. That is the power to hydrogen absorb excess renewable energy, while hydrogen to power converts store hydrogen back to electricity using fuel cell or turbines. This bidirectional capability allows a hydrogen to act as one of the long-term energy storage medium, supporting peak saving, backup power, and seasonal balancing of our grid and microgrid over here. You can see it from here, this figure, how it is going to be usable and have a diversified application over here, from storage, energy storage to synthesis, and how it is going to be generated from renewable energy through electrolysis and have application in the direction of heating, re-electrification, mobility part, agriculture, industry, even in the chemical part, it can have a e-fuel, you can have it in terms. So this synthesis, we can reduce it to carbon footprint also. Next slide, please. Now here we have the safety standards and infrastructure. If we are going to talk about that is safety and standard. So safety is central to hydrogen infrastructure. So hydrogen has a wide inflammability range, low ignition energy, and have an invincible flame over here. So mitigation measures includes the leak sensor, ventilation, pressure relief devices, optical frame detector, and intrinsic safe zones we have. So international standards such as ISO 14687, IEC 62282, and SE, that is J260, which is particularly meant for refueling, as a regulatory backbone and ensures the uniform safety and operational practices worldwide. So these are the standards which are going to be required for safety and standard infrastructure over here. So some safety operation systems we generally required over here, and based on this only, these things can able to take up to the deployment level over. So this is an building trust in the next slide here. That is the digital and the smart hydrogen infrastructure. If we are going to talk about um, modern infrastructure, hydrogen infrastructure, increasingly reliant on digitization. So, with the implementation of smart features just like an IoT sensor, AI-based prediction maintenance, digital twin of pipeline, tank, secure SCADA system, enhance the safety and reduce the overall operational cost. So, digital certification and blockchain-based hydrogen tracking are enabling to support the hydrogen trading market and guarantees the green hydrogen provenance over here. So it will going to reduce. He have a key role in reducing the downtime, improve the safety, and enables the trading part over. So that thing is going to be meant by allowing to have a next generation internet technology over here, so which we can have it in a proper way, which is going to be coupled smartly with the three, with the 5G or 6G technology, and have a complete data analysis which includes the traffic management, smart parking, air pollution, noise, everything are going to be interconnected with them. And ultimately, these things are going to be having a data set type of thing, so which is going to be controlled and make it helpful in the direction of making this thing more sustainable. So this way they can have it in the near future over here. So digital and the smart hydrogen infrastructure, which is going to be proposed by means of this slide. Please, next slide, please. Yeah, here the global hydrogen infrastructure, if we are going to talk about, globally, the Japan has the leads the hydrogen, and Europe is developing a continental hydrogen backbone. The USA is investing in the regional hydrogen hubs, and the Australia is focusing on the export-oriented green ammonia. So these initiatives demonstrate the hydrogen infrastructure development is already underway and transition from pilot projects to large-scale deployment over. So you can see it over here how the early stages feasibility studies operational has been shown over here, and here within this India is in early stage and feasibility studies has already been conducted, and right now it is in under way over here. You can see it from this figure where the triangle and the squares has been shown along with the capacity part. So if you are going to see the majority of here, we are going to have it in a square form, a little bit triangle part over here, and somehow red portion, which is we are in the early stage over here. And for that, we have to go to a blue phase where the operational one we can have it. So in other countries, we can see it over here. They are still in the operational one, and various key projects has already been demonstrated and taken up. For example, in Europe, Europe Hydrogen, that is IPECA, H2 Infra, they have. Whereas in the case of North America and Japan, Hydrogen Society dominance they are going to have. Then Asia Pacific, hydrogen, Japan hydrogen map, Australia hydrogen export, all these things they are going to have. So in terms of global hydrogen infrastructure investment, if we are going to talk about for the range of 2020 to 2050, the major investment we are going to have it in terms of production part over here. That is 4.2 trillion dollar over here. And in terms of transmission, then it will going to have a 1.8 trillion dollar. Distribution we are going to have little bit less as compared to that one, and storage we have little bit less. And lastly, the end user part, that is not, it's only the $2 trillion. So the production part is very important over here, but all the end users are still in the lower segment. Later on, it will going to rise. Next slide, please. Yeah, this is the Indian hydrogen infrastructure vision over here. So India's national green hydrogen mission targets 5 metric ton per annum by 2030. The focus is on indigenous electrolyzer manufacturing, export hub, hydrogen mobility pilots, and integration with renewable energy. So India's solar potential, coastal access, and manufacturing-based position is strongly thorough. The challenges such as the water availability and logistics must be addressed over here. So you can see it over here where the states which have considered for the deployment of to attain the national hydrogen mission over here for production of green hydrogen production. Here the green portion represents the green hydrogen production sites, where blue one shows the wind part, and the orange one shows the um, solar part, and the arrow line shows the transmission to power over. That means that it will going to be connected with the grid path. So in some regions, in some states, still is under the state, just like for JNK or Chhattisgarh or Jharkhand or Bengal part, all these things we don't have such type of infrastructure, but in near future we can have it over here. And with the realization of the unlocking the full potential of the hydrogen, definitely they are going to have this type of export hub or hydrogen mobility pilots over here. So still we are also working, and we from this triple ITDM we are also working in the direction of giving our contributing to green hydrogen mission, where we are focusing on the cleanest way to have the hydrogen production for the mobility aspect, rather than depending upon the uh, hydrogen station. We are working on the onboard hydrogen generation from the base heat. So we are working on that part also. And next slide, please. Once we are going to have this, the job awareness and job creation we are also going to have. So here the challenges associated and the bottleneck we are going to have. So the key challenges includes the high capital cost, lack of standardized infrastructure, energy losses across the hydrogen value chain, and the shortage of skilled manpower. So overcoming this bottleneck requirement, um, coordinating the policy support and technological innovation and large scale demonstration projects to drive the cost reduction, we can have it. So such type of infrastructure can be attained by leveraging the skill manpower we have to require, and that part we have to focus on the investment related to training hubs and other things, and as well as the awareness programs we have to also make it up. So these are the some key challenges associated with this. Next slide. Next slide, please. Yeah. In terms of economic analysis and policy framework, if I'm going to talk about the hydrogen storage cost arises from electrolyzer, storage, compression, transport, and operation and maintenance over here. So cost reduction pathway includes the manufacturing scale up, standardization, and declining the renewable energy cost over there. So policy instruments such as the subsidies, carbon pricing, contract for difference, and hydrogen purchase obligation plays a crucial role in the market creation and a risk reduction over here. So these are the important thing in terms of economic analysis. Here, one new term I have discussed, that is the carbon pricing. So carbon credit system has already been started in other countries. By next year, within India, we are also going to have the carbon credit policy over here. So therefore, we can trade it over here based upon the carbon also, that how much carbon we are going to that support contribute in suppressing by means of more plantation or using renewable energy and other things. By means of it, we can earn a carbon credit over here, and we can trade off with the other exports. So different trading platform we are going to have it in near carbon credit. Next slide, please. Sir, next slide. Yeah, here that economic analysis and policy framework, that policy and regulatory, if you are going to talk about that policy and regulatory infrastructure required to enable large scale deployment of hydrogen system. So it highlights the hydrogen development is not.
Sorry to interrupt you, sir, but your voice is not so clear.
It is okay right now. I am audible?
Yes, sir. Yes, sir.
Yeah. So related to policy and regulatory infrastructure requires and enable large-scale deployment of hydrogen systems. So it highlights that hydrogen development is not driven by technology alone, but strong depend upon the supporting policy instruments and regulatory framework. So key policy instruments such as the production subsidies, carbon pricing, contracts of difference are essential to bridge the current cost gap between the green hydrogen and fossil-based alternatives. While hydrogen purchase obligation help create assured demand and reduce the investor risk. So alongside this, infrastructure enables like the zoning and land access, clear safety regulations, and deliberate market creation mechanisms are critical for the accelerating this project approval, and private sector participation is going to be key. So this emphasizes that hydrogen regulation inspect the multiple domains, including the electric system, national gas network, pipeline, application, safety, emission accounting, water consumption, local pollution, all of which falls under different regulatory authority. Effective hydrogen governance therefore requires a coordination across the energy, environment, and industrial regulators to provide policy fragmentation. So overall, the message conveys that well-designed, stable, and harmonized policy and regulatory ecosystem is going to be backbone for scaling hydrogen infrastructure, ensuring the investor confidence, public safety, alignment with national climate and energy security goals. So next slide, please. Yeah, here India's specific infrastructure challenges associated with the hydrogen. So some challenges we are also having, but along with that challenges, we are also having the opportunities also. So opportunities associated with the developing large-scale hydrogen infrastructure within framework of National Green Hydrogen Mission, On the challenge side, if we are going to talk about major concern is the water energy nexus. So, green hydrogen production through electrolysis requires significant quantities of high purity water, which can be constrained in a water stressed region in India. So, tropically climate conditions include high ambient temperature and humidity, also affect the electrolyzer efficiency. So, material durability and safety issues are there, even the storage part also. So, in addition to import and export logistics for hydrogen and hydrogen driven fuels such as ammonia demand substantial port side infrastructure upgrades. So specialized handling system we have to require along with the safety protocol over. So another critical bottleneck is the skill development gaps over here. Related to this, large-scale hydrogen deployment requires a trained workforce across the manufacturing, operation, safety, and maintenance uh, domain over. So at the same time, India strong strategic advantages which we are going to have that India has the abundant solar resources. So enables the cost competitive green hydrogen production and particularly in the arid and the semi-arid region. So the presence of long coastal lines offers a natural advantage of developing coastal hydrogen and green ammonia export hubs, supporting the international trade. So furthermore, India pushes to indigenous market of electrolyzer, fuel cell stack, and balance of plant components under the initiative like an Atmanirbhar Bharat can significantly reduce the cost and create jobs and strengthen the domestic supply chain. Overall, it conveys that India faces unique infrastructure, resources, capability, and challenges. So these are counterbalanced by a strong renewable potential, policy momentum, and infrastructure capability. Um, so positioning the country to emerge as a global green hydrogen hub over here. Next slide. So here the future look and critical success factor if we are going to talk about. So future outlook of hydrogen infrastructure up to 2050 and identifies the critical success factor required to achieve a net zero system. So our roadmap structured into three phases over here. That is in the foundation phase, that is 20 to 2030, where the focus on first the commercial projects, technological validation, development of a digital standard, construction of about 5 to 10% of final infrastructure. The acceleration phase, which requires 2030 to 2040, during which hydrogen technology becomes cost effective and infrastructure scale to gigawatt level, regional hydrogen networks are going to be established. And roughly around 30 to 40% of final infrastructure is going to be built. And in terms of maturity phase, if you are going to talk about, it is in the 2040 to 2050, characterized by a global hydrogen trade, full integration of electricity and energy system, connected market, and completion of near 100% of required infrastructure. So alongside this phase rollout, the slide highlights the next generation traits such as the hybrid battery hydrogen system, hydrogen microgrid ammonia, Banarak port, defense and space application they are going. So which will shape the future deployment pathway. So the successful hydrogen transition depends on these four critical enablers: policy through carbon pricing, mandates, and streamlined permitting technology. So via efficiency improvement and material involvement, finance through risk sharing mechanism and blended finance model, and the public acceptance achieved through safety demonstration and community engagement we can have. So together, this element defines the realistic and structured pathway of hydrogen to involve from earlier adoption to the full mature global integrated clean energy system. So looking ahead, the hydrogen infrastructure will evolve through hybrid battery hydrogen system, hydrogen microgrid or ammonia uh, bunker port, and application to defense and space over here. So within in India also, here in the Jabalpur also, even in the ordnance factory also, they are also working in the direction of deployment of this hydrogen technology for their defense purpose also. So they have their different landmarks and objectives over here. So we have interacted with the ordnance factory and vehicle factory over here in terms of how we can contribute them in terms of attaining this type of infrastructure with them, and how this we can contribute in terms of national green hydrogen mission over here. So in order to conclude, that hydrogen infrastructure is the backbone that converts the renewable energy over here and renewable energy abundance to into reliability, resilience, and decentralization. So without infrastructure, hydrogen remains that without this all this infrastructure, hydrogen remain just like an experimental level at the lab scale over here. So within infrastructure, hydrogen become a transformational over here. So next slide. Here we have successfully completed. So by with this we can going to have the take off. So with infrastructure and hydrogen remain experiment. So here all these things, research and industry and government, all these things, these are the major stakeholders which have to come together for the development of this hydrogen technology from the lab scale to the deployment stage to the end user super. So we have to focus on the material efficiency, safety, and to come in the our hand users or deployment phase, government based regulatory bodies, they have to govern. So full supports needs to be given over here in order to adapt to this in the major role. So thank you. Here, next slide. I think here it is. We have completed. We have a questionnaire over here.
Does anyone have any questions? Anyone of you?
No, sir. It was good and understood everything.
Okay, ma'am. Anyone else?
Sir, you can share the Google form with the participant related to feedback, and I request you to have it to me also,
Sure,
so
sir.
that whatever the suggestions we can have it from our participants, so that we can improve our content
Sure,
to
sir.
our participants in near future. Also, we are going to focus on
Sure,
that part.
sure, sir. Sure, sir.
Yes, sir. I would like to give one feedback.
Yeah, please, ma'am.
Ma'am, sir, whenever we are presenting on the screens, like online, Sir, try to occupy the less space on your slides because आपने जो pics लगाई थी that are very good, but we have to zoom every time to see every pic. ठीक है sir, diagrams. It was
Yeah,
too
I will
much.
keep in mind. At
It was
last
too much.
moment, I have prepared that part, particularly this slide over here,
Whenever we are
because
presenting in a presentation in a hall or anywhere on a projector, it is good to have that. Then we are getting a good view. But sir, isme we have to zoom every time when you are focusing on
yeah,
something.
actually, it has not been shared from my end, so therefore some technological
No, sir.
subset we are going to have. But in near future, I will try to have it in a broader scale so that
Yeah.
related to zooming
Whenever
part, whatever the
online, try
difficulties
to
you are
have a
going to
minimum
face, I
on
will try
the
to
one
explain.
slide. Yes, sir.
Ma'am,
Okay.
actually, this is not a technical glitch. Actually, the slide screen, if you are logging through the mobile, every time the slide screen space has been limited. So that's why you have to be over there. Otherwise, if you log in through the laptop or any other projector or screen, then you no need to zoom it out.
Sir, but on laptop also the screens are small now. And some photographs where there are the complete process is there. For that we have to zoom where he is focusing particular thing. In
No,
laptop also.
no need to worry about, ma'am. We provide you the entire session PPT in the group section. Then you can proceed from there.
Okay.
Okay, ma'am. Is there any question?
Actually, here in the second one, this is entirely focusing on the hydrogen infrastructure part over here. So, related to this, that gathering all the information and the content related to this is little bit quite challenging along with that picture. So whatever the content we have got it from the research paper and try to get it in a materialized form in a using the AI over here. So related to that, some poor pictures are going to be AI generated, so therefore it's little bit difficult to get it there. I
Sir, your
understand that.
presentation was very good. Your material was very good. You explained it very good. Sir, that
I
was not
try
the
to
issue.
make it
Maybe
over
the
here
issue
that
from my side also.
a little bit difficult for me. Actually, I just came to know about this session and I have tried to my end. I call my research scholars and get it done to the contents in terms of theoretical I have get. Then I try to how I'm going to enrich that part. So even I we try to use the AI part for an have it in a more graphical presentation over there. So that thing I just going to acknowledge from my end. So because whenever we are going to use a research paper, we generally cite it, but all these things are going to be generated from my end. So that part I have there. So it's that part related to the prompt what we have get it over here. So that to make it in a materialized in form of graphical form, it's little bit challenging for us over here.
Thank you so much, sir, for taking back-to-back sessions from
Yeah.
6 o'clock.
Yes.
On the
Thank
behalf
you.
of
My opportunity to interact with all of your participants over here. I thankful the entire that organizing team over here and taking this opportunity at right now around 9 even the faculties are over here. I think they are in the campus, so they are taking the team little bit to organize to hold such type of wonderful interaction session to their participants over here. I really appreciate and all the whole organizing team. They have done the commendable work over here to gather and taking up this pain to after the working hours over here. So I understand that part over here.
we know that the time is so hectic, like from 6 to 9, but still the energy of the participants are still so high that the above 100 plus of participants are still to be online in throughout the session. It will be so encouraging to all of us as an organizing team, also to the resource person, that the whole of the session has been understanding by the also capturing by the whole the participants such a. So it's been so beneficial to all of us. Also, I
Yeah.
would like
If
to.
anybody wants to connect me, they can have my number over here 9752 005705 And my official email ID is tushar.chaudhary, tushar.choudhery@rtdmg.ac.in. And if anybody wants to collaborate in this perspective in the direction of hydrogen energy and renewable part over here, I am open from all the sides. Even in next, I think 2 or 3 months upcoming, we are also going to have a new PhD opening over here. So scholars who want to pursue or to extend their research in the direction of hydrogen, another thing, they are most welcome. And to have, we have vacancies over here. And in next week also, we are also offering the project position over here for the JRF as well as the SRF over here, which I am having right now. So soon we are going to share that the advertisement. So be in connect to over here. So thank you over here.
So it's been a humble request to you. Whatever you are saying, sir, it's been a little bit a glitch in a voice. So if you don't have any problem, kindly share your email ID to chat section. If you
Yeah,
don't
yeah,
have
yeah.
any issue,
My chat section. My phone number.
so that participant
Yeah.
get personally in touch with you. अपने पास तो नहीं है, sir. So, sir, can we conclude here?
Yeah, yeah, we can conclude.
Okay, so thank you every participant and thank you so much Dr. Tushar Chaudhary sir for taking this back-to-back session for green hydrogen. And in the first part you have told us about the what is hydrogen and how it's been useful in futuristic technology. And in the second part you will enlighten about the storage part of the hydrogen section and the futuristic and national green hydrogen mission. I hope so the all the participants get a valuable insight and knowledge from our resource person. And we, on a behalf of Sri Satya Sai University, we are really glad that Dr. Tushar Chaudhary has been taken up this lecture as a promising lecture from your side, and it's been so beneficial, so interactive, and such and so informative to all among all the participants present over here. On the behalf of coordinating committee, we are really thankful to the coordinator of this program, Dr. Sachin Baraskar sir, also the co-coordinator, Mr. Manoj Kumar Ganwani sir, and also the Dean School of Engineering, Dr. Rajan Singh Kuswa sir, and the research director, Dr. Mohit Gangwa sir, and at last the guiding and supporting us for designing this beautiful FDP, Dr. Santosh Kumar Rai sir, who has been nourishing and designing this beautiful faculty development program across the nation, through which the whole of the participant from across the nation has been joined up and can boost up their knowledge on topic green hydrogen and future of renewable energy system. And at last, now I would like to request to all the participants kindly switch on their cameras so that we take a proper screenshot of yours. Thank you everyone for joining this session. I hope so you will get a lot of information about green hydrogen, and I think so that this FDP not only increasing your knowledge but also boost of your information regarding the green hydrogen, and much be beneficial in a futuristic whatever if you are doing to be a research or whatever any kind of project. Also, we are really thankful to Dr. Tushar Chaudhary sir who has been sharing their numbers and email ID. If in case of future, if you have any kind of doubt related to research project or any kind of issues related to hydrogen as your core subject of research, you can take a help from their side. And once again, thanks to all the participants at the late night. They are joining, still joining,
Thank you, sir.
joined there in the session. Now, I'm as a host, Desh Deepak has been signing off. Good night to everyone. Thank you so much to all the participant has been participated in this faculty development program. Thank you, everyone.
Thank you, sir. Good night.
Good night, all of you.
Good night to all participants.